Throughout this series, we've taken a look at how the many different phyla of the deep play a part in sustaining the marine ecosystem. From the top of the food chain to the very bottom, these creatures maintain the structure and balance of biodiversity through how they interact with each other and their environment. But often, the most important roles are taken up by the creatures you'd least expect. These are the sponges, members of the phylum Porifera, meaning bearing pores in Latin. With over 8,500 species known to science, and colonising vast areas of the sea floor, from the shallow intertidal zone to the continental slope and the abyssal plain of the deep. Their success is extraordinary, and their importance unparalleled. They are ecosystem engineers. By building reefs and cycling nutrients, they form the foundation of many communities, and have been doing so for over 600 million years. This is the wonderful world of sponges. The basic body plan of sponges is rather peculiar. There are three basic types of sponge morphology: the asconoids, ciconoids, and leuconoids, each more complex than the last. Asconoids have a vase-like structure with a central cavity. Ciconoids are similar in shape, but possess folds within the body wall that enlarge the surface area and allow the sponge to take in more food. But leuconoids, with their interconnected system of complex canals and chambers, have the largest surface area of all. This range of body types allows sponges to occupy a few different lifestyles. Some bore down into rock, like Cleona celata. Others are encrusted on the sea floor. By spreading over a large area, they become harder to remove and are less likely to be predated. Contrastingly, erect sponges grow out into the water, often building stem-like structures to grant them access to nutrients in the water flow. The downside is that this makes them more vulnerable to predators. Sponges are the oldest and most primitive of the multicellular animals, lacking any organs or defined tissues. And yet, taking a look within, we find a range of highly specialized cells, adapted for various functions. Sclereocytes secrete sharp, indigestible bone-like spicules that give the sponge shape and prevent it from being predated. It is these spicules that determine the consistency and texture of a sponge, whether a species will be soft, rock-like, or skeletal. In addition to the sclereocytes, we find archeocytes, large phagocytic cells that take up food particles by engulfing them. But they also grant the sponge a superpower. They allow a sponge to regenerate itself and regrow from just a few cells. Perhaps the most important type of cells we find within the sponge are the choanocytes, flagellated cells that create a water current to bring in water through incurrent pores and pump it around the sponge canals. Sieve-like structures then filter out food particles and tiny organisms to provide the sponge with nutrients, before the water is pumped out via an opening called the osculum. Green dye released at the base of the sponge can illuminate just how active these sponges are, for it is thought that they are able to pump 10,000 times their own volume in water in just one day, in the process providing a vital service to the ecosystem. They fill a niche in nutrient cycling, and by making carbon, nitrogen, and phosphorus bioavailable, they play a role in facilitating habitats for other marine life. Let's take a look at the role of sponges in supporting the ocean's key ecosystems. The hustle and bustle of life on tropical reefs is renowned for its productivity and diversity. Algae photosynthesize, producing oxygen and nutrients that sustain abundant life. Corals provide the habitat with much of its complexity and have been well studied as the main reef-building organisms. But they are not the only ecosystem drivers in tropical reefs. Sponges reside here too, colourful and often monumental structures that rival corals in their diversity. They have formed some fascinating relationships with fellow residents. Many fish use sponges like this barrel sponge to deposit their eggs. Other fish are obligate sponge dwellers. But some reef organisms take this association to the next level. This is a sponge crab, a crustacean that likes to protect itself in style. Upon discovering a sponge, the crab will cut it up, shape it, and trim it down into a portable shelter for itself. With a pair of specially adapted legs that are shorter than the others, it reaches up and over the carapace to hold the sponge firmly in place. A living and highly effective shelter that acts both as camouflage and as a source of chemical defense against predators, due to the unpalatable toxins sponges produce to protect themselves. This symbiotic association is believed to be a case of mutualism, where both organisms benefit. The mobility of the crab gives the sponge a significant advantage over its fixed rock-dwelling cousins, and helps it overcome the limitations of having a sessile lifestyle. As the crab moves, the sponge gains access to more nutrient-rich currents. But while these elegant, colourful, shallow-dwelling sponges hitch a ride around the reef, a far more peculiar realm of sponges lurks in the depths beyond. In the deep sea, vast aggregations of pale white sponges cover the rocks and ridges of the sea floor. These are the sponge gardens of the deep, made up primarily of the class Hexactinellida, also called the glass sponges. They are often the first settlers to colonize many seafloor regions, providing structural complexity that creates a hotspot of life in the challenging deep sea environment. An oasis where creatures of the benthos can find food and shelter. But in addition to bringing life to the depths, these sponges also take it away. The food-poor environment of the deep sea makes surviving on microorganisms and dissolved nutrients a challenge. The constant movement of the Choanocyte cells wastes a lot of energy here, so many of these sponges have had to turn to more efficient ways of getting food than filter feeding. Many microscopic hooks line the skeleton of Asbestipluma monticola, a carnivorous sponge discovered in 2014 by scientists at the Monterey Bay Aquarium Research Institute. These hooks act like a spider's web, trapping any small fish or crustaceans that get too close. Once trapped, the sponge cells begin to grow to engulf the prey and digest it. The harp sponge utilizes a similar feeding behavior, while displaying an extraordinary morphology. it's able to anchor itself into the soft seafloor mud using a root-like structure called a rhizoid. While carnivorous sponges support biodiversity by providing habitat and refugia, the sponges of the deep that retained their filter-feeding lifestyle instead perform an important task called benthic-pelagic coupling, a process by which pelagic nutrients are recycled down towards the benthos of the deep and are made available to the higher trophic levels of deeper dwelling communities. This is made possible by the active suspension feeding of these sponges, reaching far above the sea floor and out into the flow of water, where they consume plankton and create a trophic link between the benthic zone and the midwater above. The reason these sponges appear so peculiar compared with their shallow counterparts is because the different classes of sponge display depth-related differences in abundance. Calcareous sponges are restricted to life in the shallows, as in deeper waters it becomes too demanding to produce their calcium carbonate skeletons. The white skeletal hexactinellida class reside almost exclusively in the deep. Members of the class Demospongii, however, have skeletons composed of silicon dioxide and are the most abundant of the sponge classes. In fact, about 90% of all sponge species belong to the Demospongii, inhabiting the shallows and the deep, and are sometimes found near chemosynthetic environments. Clinging to the rocks around hydrothermal vents, Asbestopluma rickettsii feeds on chemosynthetic bacteria that thrive on the superheated vent fluid. Like many epipelagic sponges, these species are thriving at an area of primary production. Sponges are an overlooked marvel of the marine environment. Their ability to bring structure and stability to barren landscapes and transfer nutrients from the water column to the sea floor supports a diverse array of deep sea communities that would not exist if not for sponges. They occupy a vital niche in every habitat where they're found, and with their range of body shapes, sizes, and feeding behaviours, they have colonised almost every corner of the sea floor. The sheer diversity, functionality, and survivability of these ancient organisms is a testament to their success. This portion of the video is sponsored by NordVPN. Proven to be the fastest virtual private network out there, NordVPN allows you to browse the web safely and securely, protecting you from online snooping and interference, in much the same way as the counter-illumination of firefly squid protects them from predators. But it's useful for more than just protection. In one click, you can connect to any one of 5,100 servers in 60 countries and be able to access websites, content, and streaming platforms not available in your own country. In addition, NordVPN is offering Natural World Facts viewers an exclusive deal. Simply visit nordvpn.com/naturalworldfacts or use the coupon code naturalworldfacts to access this exclusive deal.